about what we were talking this morning, and will tell us about lower bounds, conditional lower bounds for MPC via distributed lower bounds.
Thank you very much. So it's really a pleasure to be here again after my yesterday talk. I hope you are not bored with me yet. What today I'm going to talk about is to kind of continue the discussions you have heard earlier today by Mosen and Slobodan. I must admit that some of the things that I'll be talking today will be maybe repetition of something that Mosen said earlier, but most of the talk will be having different flavor. Okay. Again, this doesn't work. Okay, so really the talk is about limitations of MPC. Let me first so limitations of MPC were in the context of actual distributed computing, parallel computing, and correlation between those two. So first, what is really distributed computing or distributed graph problem algorithms? So we are given some network, and on the base of this network, we have in each node, we are kind of locating some processors or node, which is some computational device. You can always think it's a powerful computer. In most of computational, in most of distributed computing models, you'll be assuming that it's a very powerful device. In parallel computing, you have slightly different setting. You also are given some input graph, but actually there is no relation between the network and the computation done, in the sense that you have some parallel machines on the side. So in principle, it looks like something very similar, and in some cases, it is very similar. But in general, it's kind of different perspectives. So what I would try to present today is how some ideas from distributed computing can influence some results in parallel computing, and actually also to talk about parallel computing on its own. Okay, so first, distributed local model. I know that Mosen explained this in details. My definition is the same. So you are given you are given a network. In this network, you have n nodes, m edges. And as I said before, okay, nodes of the input graph are the processors. So these are the machines which are having some computational power. Then we place them there, and then we'll be assuming that we have synchronized system. So we are running in synchronized rounds of communication. And in each step, every node, each machine, can send whatever information it wants to all of its neighbors. So an important thing is, we are sending only using these edges. I hope you can see it here. Is the color, here is bad. Is it bad? I don't know. Good. So they can only use these edges. Important thing is, the amount of information they can send is arbitrarily large. As Mosen explained in details, it has some positive features, and the goal is to minimize the number of communication routes. Now, whenever I was working parallel algorithms, usually n and m were the inputs. In distributed computing, people also actually like to also have parameter delta, so we'll have parameter delta to be the maximum degree. Now, we also have very related model, which is congested clique model. And I think Mosen mentioned it more like in passing. It's a very similar model. So you are also given network. You are also placing machines, processors in the nodes. But actually, the communication does not have to use just the edges of the network. So we are assuming that we can use, we can send messages to any other network, to any other node in the network. So, this network was too difficult to draw as a clique, but in principle, it's a clique. So whenever we want to send information to someone, we can just send this information. There is one important difference between this model and the local model, is that we are restricting ourselves to sending messages of logarithmic size. So this is kind of, we have limited bandwidth. Now, Parallel MPC. We already heard 2 talks with definition of MPC. Each of the talks was giving slightly different definition. I'll give some other, maybe almost equivalent or maybe not. So we're given again, the input is a graph and nodes, images, maximum degree delta, and we have machines which are placed somewhere. Then we'll be assuming that these machines have space S. S is a parameter, local space on a single machine. Then next, we will have some number of these machines. And usually, when we'll be studying upper bounds, the number of machines will be something like input size divided by local space. But when we'll be studying lower bounds, quite often this will be actually any polynomial in n number. So we'll be assuming we have huge number of machines, depending on upper and lower bounds. And because here in this talk, I'll be usually focusing on lower bounds, you can think that we have any number of machines, polynomial in n. Now, this is kind of the model that many people like, and especially in practice people like. I mean, in the vanilla model, what is a vanilla model? Something that somehow would like to use as a platform to study algorithms, to study communication aspects. We really don't care about the number of machines. So you can really think that for some, so if you can show some claims for any number of, especially lower bounds, for any number of machines, even if it's exponential, triple exponential, then you are in a great shape. So some people are also using this setting. Then, so these are machines and they want to communicate. And how is the communication done? So initially, the graph is arbitrary partition among machines. I think in the morning there was a question how it is done. To some extent, you are assuming you don't want to assume anything. The graph is somehow partitioned among the machines so that every machine has capacity S, so it can store at most S bits of information or S words of information. And then these machines are doing some computation, arbitrary computation, and then in each, so that's again a synchronized system. In each round, each machine is sending at most S messages, and each machine is receiving at most S messages. And you are repeating this, and yes. And what is the goal? The goal is to minimize the number of communication rounds in that setting. Now, if you are thinking about how the system should work, to some extent, you are assuming that S is a parameter given to you. It's an arbitrary thing, actually not necessarily even related to the input size. And the number of machines is also given to you. So, if you are believing in, I don't know, OpenAI or Google, they have unlimited number of machines, and they are very powerful. So you can often think in that sense that this is something that you can imagine here. Now, again, about this vanilla model. So sometimes people are assuming that the individual machine has arbitrary memory. It's arbitrarily powerful. Think really about Google machines, okay? Or OpenAI even better. So this is something which is extremely powerful. The only thing which you are limiting is the amount of information you are sending from one machine to another. So in each step, you are sending at most S messages, and you are receiving at most S messages. In some cases, this is something which is useful. Okay, so this is our setting. And as I said, in vanilla model, you can always assume machine is arbitrarily powerful. However, normally we would like machines to be good, but not necessarily super good. So they can run in polynomial time or linear time. Without loss of generality, though, one can consider the setting that every machine is super powerful, can solve NP-hard problems in a second. Okay? So this is the setting. Yes. So this is the setting. Now, the next thing is, which has been also mentioned by Mosen and then by Slobodan, it's important to kind of think about some space regimes in MPC. So the first space, so what is space regime? We're kind of saying what is the parameter S, which is space on a single machine? How do we relate it to the input size? So in the first space regime, when S is some like n to 1 plus epsilon for any positive epsilon, this is something which people are calling superlinear space or high space. Then in this setting, as you have already seen, I think from Mosen's talk, many algorithms can be solved easily in constant number of rounds. For example, maximal magic, sorry. Then the next model is when the space is something like linear in the number of vertices, number of nodes of the input graph. And then an interesting feature, which is what I want to emphasize here, is that this model is very similar to the congested clique model from distributed computing, which I define on slide 2 or 3. In this model, we have some fantastic constant time algorithms, including problems, so complicated problem in principle, like MST. We also have some slower algorithms, and Slobodan, for example, studied this model also. Then the third model is the model where we have low sublinear space. So every machine has local space, which is n to epsilon, where epsilon is some constant between 0 and 1. This is something which, I mean, on one hand, it's very related to local model. On the other hand, great thing, what I will say in a second again, is that it can simulate PRAM. And in this setting, we do not have many constant time algorithms. But we have, so the major challenge, to some extent, of this model is to beat the PRAM, which means to do something better than logarithmic time, logarithmic number of rounds. And the final model, which I think it's important also to mention, is that we have logarithmic space. It's important to mention it and at the same time to say not much can be done. So it's really not the model that people would like to see. Now, Mosen was calling this model, how did you call it? No, you're using fully scalable model. And to some extent, in my opinion, this is the best description of this model. Because what is really happening in practice? People have some set of machines. They have some capacity. They have some local space, S. And you would like to make it independent of the input size. And if you are making, for example, assumption here, oh, input size is proportional to the number of vertices proportional to the local space, it's something quite artificial. In general, here in this model, you are saying, you know, even if my input is of size trillions, and I have just millions of local space, I can still kind of set a parameter epsilon, which will work here well. So in my opinion, this is kind of a scalable model. Okay, then my very biased view on these four models is that, I mean, that's not biased yet, but this is something which we understand very well and not much is happening. But the second thing is, you know, this linear space, it's a very interesting model, largely because people, I mean, we still have a number of interesting open questions. This is very related to the congested clique model, and would like to understand it. And this model, in my opinion, you see, this is exciting. This is very exciting. This is the model where we don't understand many things. We have some intuitions, we have some solutions, but this is something that we are struggling really big time. And the last model is just boring. So we don't pay attention to it much. Okay. What is really this talk about? I would like to we have been studying for several years, the questions, how powerful is the MPC model? And one thing which I actually found when I first time seen it, I found it exciting, is that even with low local space, the MPC model is stronger than PRAM. On one hand, you can think it's trivial. On the other hand, it's something that, you know, there is this sorting algorithm which can sort n numbers. Even if you have root of n machines, of local space root of n, you can solve them in constant time. And this is something which I think it's nice. Okay, so first of all, implication is these 3 books, these are books that people have been studying on PRAMs. So unfortunately, this volume, so this is still 3rd edition. In the 4th edition, they removed PRAMs. But in the first 3 editions, these were some 1 or 2 chapters about PRAMs. So what does it mean? If you are a programmer, you just take this from a shelf and you can design algorithms. But the underlying question here is, can we do better? And by the way, this sorting algorithm, I think actually quite a few people don't really know how to do sorting in constant number of rounds. And I remember at some moment I was surprised that some very knowledgeable people even didn't know that this can be done in deterministic constant number of rounds. So even this, on one hand, it's a common knowledge. In fact, it is not. So it's good kind of to be aware of that. But our question is here, can we do better than PRAMs? And here I will just talk for a few minutes about MPC with linear local space. And I will argue that this is the same or almost the same as congested click. And I will say what are interesting implications of that fact. And then we'll be trying to start a question, okay, we have MPC with low local space, and I would like to understand to what extent it's different from PRAMs and also from local model. And this is something like also a generic question. I think 5 years ago, I didn't really expect that there would be so close relation between distributed computing and MPC. So I remember several years ago on some conference, Mosen came to me and started talking to me about this model. And I remember I was not impressed. He was just telling, oh, there are exciting things. I was nicely, politely listening to him, you know. And then I noticed that this is really the most interesting setting, and many exciting things has been happening here. Okay, so first I would like to say about this thing. So congested click and MPC with linear space. So there is a very nice result by Hegeman and Pamaraju, and then Sohail and et al., which was essentially showing that MPC with n machines, and each machine has local space which is linear in n, is essentially having the same computational power as congested click. Now, first of all, why this is interesting result? Because people have been studying congested click for years. I mean, maybe for 10 or 15, but still longer than MPC. And this is actually interesting from a conceptual point of view, because some people are thinking in kind of parallel language, so language of parallel algorithms. Some people have this background in distributed computing, and actually bringing this together has been giving some very interesting results in the past. So these are 2 results, and I actually even have some slides, some text, what has been happening. But to a large extent, these are very simple claims, which are showing that one model can be simulated by another very efficiently without really any loss. Okay, so here, this is the second, for example, is coming just from some Lenson's routing algorithm for congested click. Now, let me also actually add 2 disclaimers, because some people are sometimes saying that these are not really the same models. There is some, so for purists, these are not equivalent models, because in congested click, even in the most standard setting, we're assuming that congested click nodes, machines, processors, have arbitrary power and are using arbitrary space. And here we are some kind saying that, you know, local space is just linear. So this is something which, if you have a congested click algorithm which is using a linear space, then these 2 models are definitely the same. If people like me are paying less attention to the local space, as I said before, the main thing is bounding the communication, then these 2 models are really the same. Of course, there is another catch, that here, you know, you are given a graph, the input graph has n nodes and m edges. And there is no mentioning of M here. We're essentially assuming that the total space is n squared. Quite often, one can actually make sure that this is still, if we have congested click algorithm, we can kind of optimize the space here as well. Okay, so what is an interesting implication? These two others are almost the same. Now, unfortunately, there is a bad news, which I think actually not everyone in MPC world does know, that so Drucker and Kuhn and Oshman, they actually show very nice thing, or very bad thing, it depends what you think. They essentially show that because congested click is sufficiently strong to simulate some circuits, proving any lower bound for congested click will have some implication in circuit complexity. So, okay, whatever, slightly super constant lower bound on the number of rounds required to compute some explicit function in congested click will have some implication on the complexity ACC, where this is kind of a big question, I mean, not as big as P versus NP, but still a question that people care about, and we don't really expect progress. So one translation is there are no lower bounds on MPC with linear space. If you are very ambitious, actually, you can think about this in a different way. You know, maybe you want to attack this complexity question by studying lower bounds in congested click. I think it's very ambitious. But you know, we have ambitious people. Okay, so some highlights. So what Slobodan, for example, was talking about, that, okay, on one hand, by PRAM simulations, we can get something like maximal matching algorithms in logarithmic number of rounds. And what Slobodan was presenting to us, that actually we can find maximal matching or good approximation of matching in log n rounds, which is substantially better than PRAMs. Now, many people do conjecture, okay, I don't know, some people maybe, or many people conjecture that log n is the right answer, but we don't really know how to formalize that. So the lack of lower bounds is really annoying. Maybe it's lower bound or maybe it is not, but then what? So maybe there are some chances that one could come up with some conditional lower bounds, or something which would give us some strong evidence that we cannot redo it better than log n rounds. Or actually, maybe we can do it in little of log n. I don't know. But this is something which I think not everyone in MPC community is aware of. The congested click lower bounds are having some implications here as well. Yes?
So what do you, short of proving a conditional lower bound, other than that, what do you accept as a progress toward this conjecture, or like evidence that this is the right answer? Like what type of a theorem, for instance, you accept that, okay, this is...
And it's a great question. I would love to know the answer to that question. So unlike in the model that I will move to in a second, here we don't really know any natural problem that most of people would say we cannot solve them in constant number of rounds. Here we don't have such a problem. But to some extent, this slide is largely exactly to address this question. Maybe there are some natural problems that we could just take. Okay, this is, once we are conditioned on this, people are agreeing, oh, this is a hard problem.
Do you have a suggestion for that?
No, not yet. I'm assuming at the end of the semester I will have many. So, okay, so this is this linear space. And then I want to move to the low local space. So first of all, I want to make sure, so in this low local space, and in general on any MPC model, there is a trivial lower bound, which is good to be aware of, which is saying that for almost any problem, almost any is undefined quantity, but for almost anything, we do require at least log base S of n number of rounds. And this follows from the fact that if you have single bit on a single machine, and you want to broadcast it to all other machines, for example, you will need something like O of S to T. In T steps, you will be able to communicate at most so many, to almost so many machines. Now, why actually have O of S? Because there are actually some tricks that you can communicate to some other machines without sending anything. So that's not necessarily completely trivial, but it's easy. Okay, so what does it mean? For example, it shows that for this first model that I told you I think it's boring. When S is polylogarithmic in N, we cannot really expect to do anything interesting unless we are happy with log N divided by log log. Yes?
What kind of tricks is that? Is it like not communicating, is sending a message?
Yes. Yes. So I think for p-rams, for example, the lower bound of complexity from the OR function, it's not log base 2 of N, it's log base something bigger. So you can compute. Valerie was here. So I think Valerie was one of the authors of the paper. So it's an easy trick, but what is also important that this is essentially, there is one trick. So you can get maybe constant 3 instead of 2, or maybe 2 plus something, I don't remember. But when S is N to delta, so I used to N to epsilon, now it's N to delta. N to delta, then it's giving us a trivial lower bound, constant lower bound. So that's kind of not useful. But I think it's actually also good to know that we have this lower bound. Okay. Now, some representative problem. So let's just start with graph connectivity. So graph connectivity can be solved in logarithmic time using N plus M divided by log M processors. And with M cube processors can be solved in log D number of rounds. And people have been studying this problem on MPC model. So on MPC, we can get the same type of results. But actually, with some efforts, people were able to show that we can obtain, okay, if we have slightly more machines, we can do this in log D number of rounds. Why I'm mentioning it? Because this is some standard thing that people have been trying to do. And looking at Cepher, this is the assumption here. So if we want to use linear total work, we are getting this plus log log N. I think so. Okay, I'm not sure anymore. It's at least M to 1 plus epsilon, but I don't remember exactly. I think already. For log N, it's already good enough. Anyway, so why I'm mentioning it? Because this is something that, okay, this is something that people have been studying, and I actually wanted to say a few words about connectivity problem, because this is the standard algorithm people are using for connectivity. If you have enough many machines, you are just doing doubling. You first compute a adjacency matrix, then you take, okay, A plus I to D, and this will be giving you information about connectivity, and you can do it in log D number of rounds. So that's something that we are teaching, I don't know, in kindergarten nowadays. So the main efforts people have been doing in MPC algorithms was, okay, can we reduce the number of machines? And there have been some nice results mentioning on the previous slide. And the main idea was to do some kind of sparsification. So take the input graph, contract some edges, and then repeat until everything fits into a single machine, and then you are done. Okay. Now, the question is, can we do better than log N or log D number of rounds? And this is something that, Mosen already spotted. But one of the first problems people have been studying was the question of distinguishing between the case that we have one cycle of N on N vertices or 2 cycles of N half vertices. And can we really distinguish between these 2 cases in little of log N time? So I remember already 9 years ago. This was FCRC, there was some workshop. So this was the beginning of MPC model. There was some workshop on MPC algorithms. And this was kind of, I think Krzysztof was giving a talk about it. This is big question. People have been trying to work for many years. We still don't really know what to do with this problem. But this is considered as a notorious problem. And kind of this also is a good thing to what Sepper said about having some problem that almost everyone agree that it's difficult. So, however, as also Mosen unfortunately mentioned, it's known that we cannot really come up with a lower bound for this problem. So in a great paper by Ravgardner, Vasilievitsky, and Wang, they show that unless you are fantastic, you are aiming at Turing Award, there is no hope for MPC lower bounds. So there is a result so essentially they show that you can simulate on an MPC any Turing machines or circuit with appropriate size, which would imply that if you can come up with a super constant lower bound, that you would prove that P is not equal to NC. Or actually, the exact result is even NC1. Okay, so here's the statement, but I would maybe skip it. So, okay, so this is the result. We already know how things like that are done in complexity. So if you have some hardness result, you know that something is difficult. So you are just trying to say, okay, let's just take this problem as a proxy and let this be the problem that we are conditioning on in some lower bound. So because many people believe that this problem requires log n rounds, people have been trying to make conjecture on the base of that. So now we have something that it has different names. It's connectivity conjecture, 1, 2 versus 2 cycles conjecture. It's saying that this requires logarithmic number of rounds.
But what about like basing? There are some things in P that we suspect is not in NC1. What about basing that something, basing it on that assumption? Let's say that ST connectivity cannot be in NC1. Or that KRW conjecture is correct.
We could come up with other conjecture, I agree.
No, conjectures that are established in the circuit complexity world.
Yes, but this is just something that someone proven and we're happy with that. What I'm saying is, to some extent, it is. So I'm not sure what you're saying, that would like to say instead of P versus NC, would like to base on something different.
Yeah, or maybe some concrete problem that is conjectured to be outside of NC1.
Oh, actually, it's NC1. I think it's actually a gap between NNCK and NCK plus 1. So it's, to some extent, it's an upper bound, if you think in that way.
Right.
What we're saying is, this, if we could come up with a lower bound, this would imply the other claim. But maybe it would also imply some other complexity claims. So
no, I'm saying in that direction. Like, is there a conjecture about some circuit lower bound that would imply the MPC law?
I think that P is equal to NC1 most likely would imply that.
No, so I'm saying that.
I know what you're saying. I mean, I don't know. So I actually think that in general, not many people have been studying complexity implications of these results. And usually, so I have seen maybe two, no, maybe more than two. But usually, people are interested in this big thing and going into more complexity classes.
No, so this would imply
I know.
Circuit low bounds. I'm asking in that direction.
I think that, okay, I don't know. 1 versus 2 cycle conjecture. It's a great conjecture. So there is actually one thing here that I didn't really specify exactly what I mean by that. So first of all, some people believe that, okay, definitely constant. There is no way we can get constant. I think some people, I'm sure minority, could say maybe it's log n of log n is possible. There are some reasons why something of this sort could be true potentially. And then I here never mention what is the number of machines. And people are saying with any polynomial number of machines, this conjecture should hold. And actually, maybe it's hold even for arbitrary number of machines. Sorry?
If you have exponentially many, I'm pretty sure if you have exponentially many constant bounds, you can solve.
So they have a very nice result that in an MPC model, if you allow that you can send to any number of machines, this is not true. So what I'm saying, if you have S, your outbound is S, and inbound is S, that they did not have this result. They were saying this was this fan-out net circuits. So this was assuming that one direction is unbounded. From what I remember, I'm quite sure that, I mean, if you think about that, if your limitation is S in each direction, you can send S messages and you can receive at most S. That unlimited number of machines doesn't seem to help you much, in principle. So maybe, yeah. Anyway, what I want to say is that even these much weaker bounds are still exciting, and you can rely on this. Okay, anyway, I should speed up.
Is the fanning bounded? Or
Both. I mean, it depends, but I said that you can send at most S messages, you can receive at most S messages, and in the model that I was kind of defining, also your local space is S.
Are you saying that's known or unknown? This is just getting non-constant.
What I'm saying is that also with these assumptions, this is an interesting conjecture.
What is S?
Sorry?
What is S in this conjecture?
Oh, sorry, S is always n to delta.
Right, thank you.
So if you don't like delta, think root of n.
Thank you.
Yes.
So
So what I'm saying is
that
the same conjecture. So this conjecture.
that's the conjecture, I understand.
Yeah. So that's one conjecture, but I didn't specify how many machines they are.
Right.
Often people would like to say, okay, with linear number of machines. The same conjecture most likely holds with any polynomial number of machines. And the same conjecture, so the same most likely, it's difficult if you have arbitrary number of machines. And I think if you base on any of these variations, it's interesting. Okay, let me move forward. Oh, so for example, I asked this question, can we do better than log D or log N? And one can show that we cannot. So, and actually here, okay. And this is actually maybe the biggest, or one of the biggest questions here. I mean, it's a very ambitious question. So what is really the complexity of 1 versus 2 cycles? So maybe actually one can beat log n, maybe one can get log n over log n. Many people believe that you cannot. So can you kind of formalize this limitation? Anyhow, can you come up with something, as you were saying, better than P versus NC, or I don't know what? Okay, and for example, so this is, I have taken this from a paper. So this is a list of problems which are equivalent to 1 versus 2, I don't know. And this is an old list. So nowadays, people have been studying many problems and were saying, oh, this problem is equivalent to some other problem, to 1 versus 2 cycle conjecture, the complexity of this problem. Okay. Oh, good. So now why I also mentioned this connectivity problem? Because one way of seeing this algorithm is that to some extent, what we would like to learn is we would like to learn the hop neighborhood of a node. So you are given a network and you would like to, I mean, this matrix multiplication algorithm is just doing nothing else, but learning some information about the neighborhood, the hop neighborhood. And if you or to some extent, what these papers were doing, they were trying not really to learn the whole D-hop neighborhood, but learn an important part thereof. So they wanted to see what are important edges which want to maintain, or maybe some connections. So this is kind of the way how people were studying this. But because of that, one way of seeing these algorithms is some connection to this local model. So as Mosen described this model to us before, this is just a model. So T-hop, this is model which essentially is saying, okay, I can solve a problem in T rounds if only if it's enough for me to see the entire T-hop neighborhood. So people have been studying the question, what is really the relationship between these two models? And one way of seeing this MPC is something where a single vertex can learn its entire T neighborhood in log T rounds. Okay, so to some extent, the idea is that maybe MPC can simulate local algorithms in log T rounds. And there is a very nice case, which I always like. So I hope you are all familiar with this algorithm, maybe not. So there is a fantastic algorithm for coloring, 3 coloring on a ring. So you're given a graph with maximum degree 2. You want to 3 color it. And Cole and Vishkin, they show actually that you can solve this problem in log star time. So then actually, their algorithm was relying on log star neighborhood. So one can transform this into local algorithm, which is relying on log star neighborhood. And with this, we can easily obtain an MPC algorithm, which will have complexity of log star. Why this is possible? Because we can learn T-hop neighborhood. T-hop neighborhood, when T is log star, will have size 2 to log star, which is still less than n to delta. Yes? Sorry?
It's a line, right? It's a ring, so it will actually be linear, the distance, the size. It will not be 2 to the log star, it will just remain log star.
It will be still log star in local?
I mean, the size of the neighborhood, right?
Size of the neighborhood is linear?
Just because it's a path, right? So the size of the neighborhood remains linear in this case. With the neighbors.
No, but local algorithm, local complexity is log star.
Yes. No, like the implication is correct. I'm just saying the size remains linear.
The size in T rounds would be 2 to T.
No, just T.
Just T then. Oh, yeah, sure. Yeah, because it's a line. Yeah, okay, I agree with that. Yeah, sorry. With that, I agree. I didn't want to go into, yes. So this is a fantastic result. However, in general, we can just try to simulate it. And the main problem is that T neighborhood may be too large. That you are looking at your T neighborhood, you can check your neighbors, but then you would like to collect all of them. And there are just too many of those. So this is a challenge which have been discussed here. And in fact, there are very, very few problems that we can match this bound. Okay, now I want to move. So people start the question, okay, can we implement local T rounds algorithms on MPC? It's often difficult, but for example, Mosen, I think, show us that for some problems, we can do something slightly worse. And can we really formalize the relation between the local model and MPC? And there was a conjecture that, if we have T rounds local algorithm, maybe we need log T rounds in the MPC. And because of this result by Ravgat, Vasilevitsky, and Wang, we know we cannot hope for unconditional lower bounds. We will try to come up with some conditional lower bounds. Okay, so several years ago, Ghaffari, Kuno, and Oito, 2 of them are here, came up with some arguments showing essentially the following. You take any natural randomized MPC algorithm, and they show that it cannot do better than log of local number of rounds, assuming 1 versus 2 cycles conjecture. So they said, okay, natural algorithm is component stable. And component stable is informally something which it behaves, so essentially the whole behavior is focusing on connected component on a given vertex, on a given node. So you cannot communicate with nodes from other connected components. There were some issues with the proofs. So with some other people who actually polished the proof, and we extended this to deterministic algorithms, also to get bound depending on delta. So for the remaining 20 minutes, I will try to present this. Okay, I will actually try to be slightly. Okay, I'm running out of time. Okay, so this is really what this result was saying. You have a graph problem which has some round complexity in the randomized local model, and then complexity is at most log n, and then there is no algorithm which is better than log t of n rounds on low space MPC, unless the 1 versus 2 conjecture fails. Okay, I have a few slides talking about some issues with the, I mean, not some things about this algorithm. So first of all, the result was only for randomized algorithms, and it was only in terms on n. So we actually were able to fix this in the sense that it also holds what deterministic bounds, and the dependency may be on delta, which is what people in distributed computing often like to see. Then the second thing is, it is conditional on the 1 versus 2 conjecture, which is just conditional lower bound, which is a weakness. And the final thing is that it applies only to component stable algorithms. And in the paper, they wrote this claim that, you know, to the best of our knowledge, all algorithms, all known algorithms are component stable, or can be easily made component stable. I remember the first time I've seen that paper, I thought, well, that's true. Now I don't think it was true. Many algorithms are not component stable, but to see this is not always obvious. So I think this was a very good assumption, but what I'm saying is one should be careful because many algorithms are not really component stable. So here is a definition. As I'm saying, it's Polish definition and it's still incomplete. No, this one is complete. Algorithm is component stable if only if for any node, any output node, its behavior depends only on the topology of the network, only on the IDs of sorry. Okay, one by one. It depends only on topology and IDs of all nodes in its connected component. It depends on the vertex itself. It depends on the exact number of nodes and the maximum degree. And actually, it depends on the random seed, which is shared among the machines. So in short, that the output can be expressed as a deterministic function, because here we have these random seeds. And here's the theorem, as I'm saying, slightly Polish theorem from the follow-up paper. Oh, sorry, yes.
What did you mean by names in the last slide? But independent of names?
I know. It's something that we may want to have the same names in different connected components. We may allow that.
What is name?
Sorry. Okay, no, I think that this, so I don't remember details, but this means that IDs is clear, and then you are saying independent on the values on the relation between the IDs. I mean, so some info, okay, so ignore this independent of names, but somehow independent on the IDs. And here's the theorem. And the theorem is saying condition on the 1 versus 2 cycles conjecture for some problems. And we had this specific formal notation of some problems. And as you see, this some problems, it's something technical, but most of problems are in that category. But we have some formal definition. It would be few slides to define, so take it easy. We have the claim that we wanted to have. If we have an algorithm running in, lower bound for the local model, then we also have appropriate lower bound for the low space component stable MPC algorithms. And this holds for both randomized and deterministic. Okay, now the question one should ask, does it help for this node to use information about nodes from other connect components? And in principle, it sounds, often it doesn't. But actually it does. But to some extent, so what we have shown is that there are some non-component stable algorithms which are more powerful. We came up with one generic technique which is giving us some algorithms which are in that category. But maybe there are more techniques. And to some extent, the main idea is we can break this component stable scheme if we are coordinating things globally. Our approach was to use method of conditional probabilities or expectations, or in short, de-randomization, to obtain algorithms which are breaking this component stable feature. So let's just take a toy problem. You are given a graph of maximum degree 2, and you want to find a large matching in this graph. Okay. It's a very nice, simple problem. If you are happy with randomized algorithm, it's easy to come up with an algorithm. You randomly toss a coin for every edge, you take this edge with probability half, and then you are looking at independent edges, and you will get a matching of size, I don't know, maybe n/4 or something of this sort. That's easy. For deterministic algorithms, there is a deterministic lower bound, which is saying you cannot do this in a constant number of rounds in the local model. So I'll just show you how one can come up with an algorithm that can solve this deterministically on MPC in constant number of rounds. And I will be faster with some parts, but what can we say about this randomized algorithm? This randomized algorithm is relying on 3 wise independent random variables. So you want to remove each edge with probability half. So you are flipping a coin. You see, okay, so these 2 edges have been flipped, and they will form the matching. And now the point is that 3 wise independent hash functions or random variables can be represented using n cube number of of seeds. So there are families of 3 wise independent random hash functions or random variables which are of size n cube. And now actually the whole story is as follows. We want to find one such good hash function or random variable. And so we take this family of size n cube, and we are able to find an element which will be appropriate, which will be corresponding to a large matching in a constant number of rounds. And I have slides for that, but I don't have time unless Clement will give me half an hour. So what we are able to do, I'm joking, just 20 minutes would do. So what we are doing, so we have this family of n cube elements, and we are just revealing, so this has 3 log n bits, each element from this family. And we are kind of revealing these bits in some batches. And in MPC, actually, we can do it in constant number of rounds. So, okay. So I'm assuming you are familiar with the methods of conditional probabilities. If not, it's a fantastic method, and you should get familiar. So what is really happening here? So we have n cube variables. We have n cube elements And we know that on expectation, they are actually having some good feature. In our case, we'll have a matching, correspond to matching, which is of linear size. So now we want to find one element from this family. And what we're doing is, we're looking at the whole space, we're partitioning this arbitrarily, and now we know that in one of these parts, there will be at least average or expected value of the matching will be at least linear. And we'll be able to find such an element. Okay, so what we're doing it, we're partitioning these bits into chunks of size log base 2 of s, which happen to be logarithmic. And then we know that we can put on a single word all possible combinations of these bits. And then we are taking these bits and we are saying what will be the matching size corresponding to these bits. And in short, what we are able to do, first we are able to compute these bits where the average will be bigger than expectation, then we reveal it, and so on and so forth. And here are more detailed description, which I would just leave on the slide. Yeah.
You are doing all of this to reduce the number of machines or rounds?
No, round. No. I want to find one good hash function.
Yeah, but if I had n cube machine.
No, okay. I want to do it on linear. Yes, you are right. If I have n cube machines, I just do it in an easy way. Okay, let me actually say the main claim. We can deterministically find a linear size matching, which contradicts kind of the component stable thing. And this algorithm is highly non-component stable.
So how many machines, do you? Because as you said, like n cubed is trivial, so what?
Most likely we have n over s machines.
Okay.
I think so. Yes, n over s. Okay, so to some extent, the main message here is coordination may help, and we can break local barrier for deterministic algorithms. Here is another example. This was a toy problem, but MIS, for example, we have a graphs with maximum degree logarithmic. There are some deterministic lower bounds, which is showing this is what we need on the local model deterministically. But here actually we're using something similar but different. We're taking a randomized algorithm, and we know that there are some log-n rounds, local algorithms, and we can actually obtain them on MPC with such a complexity, so triple log n. And then we're able to de-randomize them. So we're using some de-randomization tricks, and we're able to get triple log n algorithm on MPC, which is beating this lower bound from the local model. Okay. I'm running out of time, so let me. Oh, and actually, so we have been also thinking, can we do it for randomized algorithms? This is more tricky. We still have one bound that we are showing, demonstrating that for randomized algorithms, we also can beat this scheme. I think I have 2 or 3 slides, so I hope I still can leave. So this is kind of a summary of the result that I kind of was saying. Now, are these bounds useful? This is tricky. So, one thing which, for example, has been annoying me in the past, I remember I read some paper in introduction that was saying, there is a local lower bound, and this implies for component stable algorithms, MPC lower bounds, so this is a lower bound. They even didn't mention it's in condition 1 versus 2 cycles conjecture. So formally, actually, this is a very tricky thing. So I would think, so first of all, formally, we have bound for component stable algorithms. Why are component stable algorithms everything? We don't really know. We actually have proofs that sometimes we can beat this bound, so that's kind of complicated. So to some extent, one should read this. We have some conditional lower bound for some special type of algorithms. This is definitely something useful. But to me, nowadays, really the main message is this is giving us good intuitions. But is it a lower bound? It's tricky. There is a great question. Can we go beyond component stable algorithms? Can we have conditional lower bounds, saying for any algorithm, we have some bound? Even though we know that, we have to do something else than just compare to the local model. I think that's that. That's all but last slide. So the final thoughts, they are great MPC. MPC model is great. We have fantastic algorithms, fantastic people who have been working. However, the limitation of MPC is very tricky. We don't have unconditional lower bounds. There are some conditional, but they are kind of. So, yeah. And to some extent, I think that the congested clique model, is there any natural problem that we can condition the lower bounds on? I think it's a great question. And I don't know the answer. Okay. And of course, can we really show that lack of component stability can help a lot? Right now we have some problems, but maybe it's a more general phenomenon. Thank you.
All right, so we have time maybe for one quick question. Otherwise, there is the coffee/tea break, and Artur is going to be there if you want to ask him all the questions you don't get to ask now. So, anybody has a quick question?
I see coffees too.
Just long questions.
Coffee is.
All right, let's thank Artur again.